integration, this along with differentiation makes up the field that is known as calculus. If you haven't watched my first video series on differentiation, then I strongly recommend that you do so before you watch this second series on integration. Obviously this is going to be the first video in the series and just guiding you through the structure of this video. Number one, we're going to be looking at the basic principle underlying integration and how it's the opposite of differentiation. Part two, we're going to be looking at some basic examples of integrating simple functions. Part three, we're going to be looking at some finer points of notation. And then part four, we're going to be looking at what happens when you need to integrate an expression involving multiple terms. Okay, so let's make a start. Now, if you think back to our work on differentiation, what differentiation allows you to be able to do was work out your first derivative from a given function. So more often than not, your original function, your original equation is going to be expressed like this, where you have y expressed in terms of x. And what differentiation allows you to be able to do was work out your first derivative, your gradient function. So just applying our rules here, you bring your power to the front and then decrease your power by 1, so that 2 now becomes a 1. And this was differentiation. Now, when I say integration is the opposite of differentiation, what I mean by that is that integration allows you to work out your original function from your gradient function, your first derivative. So say I was given dy by dx here equal to 2x. So just remember this 1 that I've got up here, you don't really need to do that. Anything to the power of 1 is just by itself. You'd never need to write 1 as a power. So dy by dx equals 2x. What integration allows you to be able to do is work out your original function, so y equals blah, 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 when you've been given your gradient function, your first derivative, like we've been given here. So you might think that, okay, if y equals x squared, my first derivative for that function is 2x. Well, if I'm given my first derivative, my gradient function, then surely my original function has to equal what we've got up here, y equals x squared, if we're going back the other way and it's the reverse. This isn't strictly true because consider this. So this is what we had originally, y equals x squared dy by dx equal to 2x. Now what happens if I have y equals x squared plus 1? Okay, what's my first derivative in this case? Well, you just differentiate these term by term. So x squared, differentiating that with respect to x, I get 2x. What happens when I differentiate this constant? It just disappears. Okay, so not only is it the case that my first derivative equals 2x when y equals x squared is my original function, when my original function is y equals x squared plus 1, my first derivative is also equal to 2x. And this is going to be the case when I differentiate anything in the form x squared plus or minus a number, constant term. So I could have, say, this, y equals x squared minus 17, and again, your first derivative, dy by dx, would equal 2x. Okay, differentiating this first term here gives me 2x, differentiating my constant term gives me 0. That constant term just disappears. Yeah, so when it comes to integrating, you can express each of these functions here as y equals x squared plus c. So we're saying that when our original function is in the form y equals x squared plus a constant number, so this could be plus 1 here, minus 17, minus 496, etc., then my first derivative, dy by dx, equals 2x. And this is something that students will forget time after time after time. I've been teaching maths for far too long now, and I also forget to my plus c here. But when you're working out what's known as an indefinite integral, which is what we're working out here, we'll look at definite integrals at C2. When you're working out your indefinite integral, i.e. you're given a question, you're given your first derivative like this, and you need to work out your original function, then you need to add in your plus c term here. If you just wait for after the jump, we'll look at different, so we're looking at a quadratic expression here. We're going to look at integrating different types of term just after the jump. But the first point that I wanted to make in this original section of the video is that differentiation is essentially the opposite of integration, and when you're integrating you need to remember to add in your plus c term here. Okay, so part 2, we're going to be looking at integrating a few different types of basic functions. So previously we had this, dy by dx equal to 2x, and we just showed from inspection, if you like, that your integral for that would be y equals x squared plus c. Y equals x squared plus c. And remember we were saying that integration is the opposite of differentiation. So just remember with differentiation, you have 2 steps. So if I'm differentiating this, 2 steps, I'm just going to get rid of that plus c to begin with. Differentiation, essentially you multiply by your power. So in this case, I'm bringing my 2 to the front, and then I'm decreasing my power by 1. So this 2 now becomes 1. I don't need to write that up there. Integration is the reverse. So rather than decreasing your power by 1, we're now going to increase our power by 1. So that's step number 1. You're going to increase your power by 1, and then you're going to divide rather than multiply by our new power. So this is what it looks like. So dy by dx equals 2x. Y is going to equal, well, this is going to stay the same, 2x to begin with. Now, so the power on this is 1. We need to raise our power by 1 to begin with, so that 1 now becomes a 2. Now we're going to divide through by our new power. So divide through by 2. Okay, gives me that. Oh, and then I told you, I knew I'd do this. Okay, just a learning exercise. And obviously this is going to be plus c. So don't forget your constant term there. And now we notice I've got a 2 on the top and 2 on the bottom. Those 2 cancel. It just leaves me with y equals x squared. So 2 steps, you're going to raise your power by 1 and then divide through by your new power. So say that's our first example. We'll go through a fair few of these. So dy by dx, next one we're going to look at equals x cubed. Our y, so raise our power by 1. Okay, and then divide through by our new power over 4 plus c. Always remember your plus c. Okay, so that's what happens when you integrate dy by dx equals x cubed. It gives me that. Another example now. Okay, rather than expressing this in terms of dy by dx and y, say, I'm now going to express this using our function notation. So just remember our function notation, our first derivative, okay, if our original equation is expressed in terms of y's and x's, then your first derivative is going to be dy by dx. Whereas if we're working in terms of our function notation, i.e. f of x, then our first derivative is going to be expressed like this. Okay, so my first derivative, the one that we're going to look at now, is going to be f dash of x equals 4x to the minus 6. Okay, now rather than working out our y, we're obviously going to be working out our f of x, our original function. So in this case, steps are going to be exactly the same. What do we need to do? We need to increase our power by 1. So this minus 6 now becomes a minus 5. And I'm now going to divide through by our new power, minus 5. Don't forget your plus c. Okay, and then just tidying this up. So I mean, generally it's good practice if you have a fraction, i.e. a fully formed fraction where you have a numerator and a denominator like this, it's generally good form to take that fraction out and put it at the front. So here I'm going to have 4 over minus 5 or just minus 4 over 5. Just remember, if I have this, it's convention to write it like this, where you have your negative sign at the front rather than on the denominator of that fraction. Minus 4 over 5, x to the minus 5 plus c. So the next example we're going to look at is this one. So if I'm given a first derivative, dy by dx equal to minus 2x cubed. So we're going to apply exactly the same rules to get back to our original function. I'm going to start off by, this stays the same to begin with, raise my power by 1, then divide through by the new power, which in this case is 4. And now just a quick note on this one, so you can see here that, again, I can take out a fraction similar to this example up here, and that fraction is going to be minus 2 over 4. Then next to 4 stays here, and then obviously here you can simplify that fraction to minus a half. Okay. A couple more examples. So this one is going to be a fractional example. Let's use our f dash of x notation here just to mix things up a bit. So just remember this is our first derivative as with the previous example, and in this case the first derivative that we're going to be looking at is minus 7x to minus 1/3. You can see the reason I'm giving you this example is that we have a fractional power, and when this is the case, exactly the same. You just need to be a bit more careful when you're raising your power by 1. So minus 7x there stays the same. Raising this power here by 1, my minus 1/3 now becomes positive 2/3. So minus 1/3 plus 1 equals 2/3, and then obviously I'm going to divide through by that new power. Okay, so now here, what I have is essentially, let's look at this down here. So if I have, I'm taking out this fraction here, so essentially what you have is minus 7 over 2/3. We'll look at this in longhand to begin with. So essentially I have minus 7 divided by 2/3, and you know when you are dividing fractions that all you do is you flip over your second fraction and your division here becomes multiplication, so that becomes times by 3 over 2. What does that give me? Well, I'm going to have minus 21 on the top, denominator stays the same, so essentially minus 21 over 2, just dealing with this part here to begin with, so that minus 7 and that 2/3, x power of 2 over 3. But if you have a look at what I've done here, going from here to here, one thing you can do is just memorize the fact that if I have a single number on the top, fraction on the bottom, all I'm going to do is essentially, you can see, kind of flip this over and then multiply the top. So essentially multiplying this one by this one's giving me minus 21, and then that 2 stays on the bottom. So all I'm doing is multiplying whatever's on the top of a fraction by the denominator of this fraction on the underneath there. Okay, last example we're going to look at. So we've seen what happens when you integrate a linear term here. So my 2x there, it became x squared, i.e. this linear term became a quadratic term when I integrated. What happens when you integrate a constant term now? Let's use our dy by dx notation here. So dy by dx equal to 5. Okay, what does my y equal? Well, I want you to think about this constant here. Rather than thinking of it as 5, I want you to think of it in terms of 5x, and now there is actually a power on this x. It's not 1 obviously, because that would mean that your dy by dx does equal 5x. Let's write it like this. So dy by dx equals 5, which also equals 5x to the 0, because just remember, anything to the power 0, x to the 0 will equal 1. Similarly, 3 to the 0 would also equal 1. So anything to the power 0 equals 1. And in this case, I've got 1 times by 5. This does indeed just equal 5. Now, if you look at it in this way, if I follow my rules and I raise my power by 1, I now have 5x. Essentially, I would have a 1 up there. I'm not going to write my 1, and then I divide through by my new power, and it would just leave me with 5x to the 1 over 1, or just, let's write this out for completeness, or just 5x. So, important thing to take from this is that when you are integrating a constant term, it's then going to become a linear term. So you're going to actually reintroduce an x back into that function there. Okay, so just a quick point on notation now. Up until now, we've been looking at integration where you've been given a first derivative, expressed either as dy by dx or f dash of x, and then the question has asked you to work out the original function. So in this case, it's obviously going to be y, and you're going to have an expression in x on the right-hand side there, or in this case, when you're using your function notation, obviously if you're given f prime of x, you're going to be working out f of x, and then again, you're going to have an expression involving x on the right hand side there. But there's actually specific integration notation that you could use as an alternative. So here we've got dy by dx equal to, say, 2x squared. You know, to work out your original function here, you're going to integrate this right hand side with respect to x. So i.e. you're going to have y equals raise my power by 1, divide through by my new power, and obviously don't forget your plus c there. I can actually rewrite this question in another way. So like I said, we were here, going from here to here, we were integrating this expression here with respect to x. So another way of writing this is using my integral symbol. So this tells me I'm going to integrate expression 2x squared with respect to x. So important things to note when you're using this notation. Obviously this is your integral symbol here. This is the expression you're going to integrate, and this needs to stay in brackets. That's very important. And then obviously with respect to x here, and then just finishing off the question, you'd have exactly the same thing we had up there. Okay, so applying your rules, raising your 2 then becomes a 1 and dividing through by your new power, plus c. Okay, and then we'll go through one more example. So say now I wanted to integrate an expression involving s. So again, your integral symbol, whatever you're going to integrate needs to stay in brackets. The whole expression needs to stay in brackets. So in this case, we're going to integrate 4s cubed. And then now we're working with s's, so we're going to be integrating this with respect to s. So rather than having a dx, we're going to have a ds here. And then following our rules, so raise our power by 1, that 3 becomes a 4, divide through by a new power, plus c, and then just cancelling those 4s, I'm left with s to the 4 plus c, and that would be my final answer to that one. So not particularly taxing, it's just a really important thing to remember here. Two things: when you're using your integral symbol, whatever expression you're integrating needs to stay in brackets like this, and also you need to have the variable that you're integrating with respect to. In this case it was an s, in this case you're integrating with respect to x. That needs to go next to that expression in brackets there. Integrating multiple terms now. So as with differentiation, if you have an integral now that is split up into multiple terms, either added or subtracted from one another, then you're going to integrate each of these terms individually. So say, again, we're using our integral symbol here, our integration notation. So we're going to integrate 2x to the minus half plus 3x to the minus 2 minus 7. We're going to integrate this with respect to x. So looking at our first term, I'm going to integrate this one here. 2x to the minus half then becomes 2x. That minus half becomes positive a half, dividing through by a half. Next term, plus 3x to the minus 2. Obviously that minus 2 then becomes a minus 1, divided by minus 1. And then lastly, got minus 7x. So just remember your constant term becomes a linear term when you integrate it, plus c. And just with that one, so we've got minus 7. Essentially you have minus 7x to the 0. So if I'm integrating that with respect to x, then that 0 becomes a 1. And then I'd be dividing through by 1, so you don't need that. It is just minus 7x. Just remember your constant terms become linear terms when you integrate them. And then just tidying this up, obviously look at this first one. We don't like to have fractions within fractions, So using our rule, essentially you're flipping this fraction over, so you know in terms of your x component it's going to be x to the half, but dealing with this bit here, so your 2 divided by a half, you have, that's the same as 2 times by 2 over 1. So just remember, when you're dividing fractions, going to change this division to a multiplication, flip that second fraction over, which gives me 4 over 1. So just remember the shortcut there, which is 4. Shortcut there is, all you do is, whatever the denominator of this fraction here is, you times this by whatever's on the top there, and then that 1 stays the same. So in this case, you've got 2 times by 2, which can be 4 over 1, just 4. And then again here, we've got 3 over minus 1. We don't like to have a negative on the bottom of our fraction, so I'm just going to essentially move that to the front. It'll be minus 3x to the minus 1. And then don't need to work on that term there anymore. So that's my completed integral there. We'll go through one more. Okay, so in this question we're saying that our first derivative, our gradient function that we were given in the question, is x to the half minus x cubed plus 4x, and then we want to work out y. We want to find the original function, so we're going to just integrate each of these terms one after another. So here, raising my power by 1, that half becomes a 3 over 2, obviously dividing 3 by 3 over 2, minus x to the 4 over 4 plus 4x, essentially that 1 becomes a 2, dividing 3 by 2. Now I'm tidying up these terms term by term, so I'm dividing through by 3 over 2, oops. So essentially I'd have a 1 on the top here, so kind of bringing this 2 onto the top would leave me with this. Okay, so just remember, when you have a fraction within a fraction like this, the numerator stays the denominator of the fraction, and you're going to multiply this denominator here by whatever's on the top. So in this case it was a 1, so 1 times by 2 gives me 2 up there. This second term's fine. I could rewrite this as a quarter x to the 4, but that term generally accepted as written in conventional form. And then last term here, oops, I've got my plus c. I told you, you will do it. I do it myself. 4 over 2, obviously cancels to a 2, x squared plus c. And that is your final answer. So just remember, when you're dealing with multiple terms in a single integral, so these are added and subtracted together, you need to integrate each term by term. And don't forget to subscribe for more tutoring videos. Remember that full notes and other resources are available on my tutoring website at idktuition.com. And if you'd like me to cover anything in particular, please leave me a message in the comments below or on Twitter at TomDavies32.